All right, everybody, welcome back. Happy Friday to you. Let's see. Before we get started today, before we get started today, we need to take a minute and review some basic probability. So we're going to imagine that we are in the observation tower of General Grievous's ship during the attack on Coruscant, and Palpatine is trapped in the chair. Anakin has cut off Dooku's hand and is waiting there with his two lightsabers to cut off Dooku's head, and Palpatine tells him, "Go ahead, Anakin, kill him. Do it," right? And instead of giving in right away, Anakin says, "Well, I'm not sure what I should do. Maybe I should, maybe I shouldn't." And then a hold off from one of the earlier prequels, the little blue flying guy Watto comes in and he says, "I happen to have a chance coin right here that you can flip to decide whether you're going to turn to the dark side and kill Dooku or not." So Anakin says, "Okay." And he takes a hold of this coin, and there's heads on one side, tails on the other. Because this is my story, it's George Washington on one side and the U.S. Eagle on the other. Don't know how it got to a galaxy a long time ago, far, far away. Maybe time travel. In any case, Anakin starts flipping the coin. And heads, he goes to the dark side. Tails, he doesn't. So we've got heads here, tails here, and we've got number of observations here. Let's see. Maybe heads, did we say he goes to the dark side? He doesn't know he's going to become evil, but Vader. And then tails, happily ever after. I don't know. What do we do there? Smiley face, no Darth Vader. Actually, that'd be kind of sad. In any case, number of observations on the y-axis. So he flips once. It's heads. Good, Anakin, good. Flips again. It's also heads. Palpatine starts cackling. And over time, though, what should we observe? About the same, right? And instead of if number observations, we put percent observed, it should be 50-50. 1-to-1 ratio, right? Okay. So at that point, Anakin's like, "Well, I still don't know what to do." And so Palpatine says, "Well, Dooku's still here. Maybe he should flip a coin too." And so they get a coin for Dooku, but he says, "I don't have any hands." And then Palpatine says, "Well, are you a Sith Lord or not? Just use the Force to flip the coin." And so everybody decides that's good, and so Dooku stands up, and with his Force powers, he flips coins as well. And because he's an honorable man, he doesn't cheat and tilt it one way or the other. So now you have two people flipping coins, and let's describe the various possibilities that we might see happen, right? So Anakin and Tyrannus. Anakin could get heads, and Tyrannus could get heads. Anakin could get tails, and Darth Tyrannus could get tails. Some of you have no idea what I'm talking about. Who the heck is Darth Tyrannus? That was Dooku's Sith name. Keep up. Then Anakin could get heads, and Darth Tyrannus or Dooku could get tails, and then maybe it could happen the other way, tails and heads. Those are 4 different outcomes, though from our perspective, in terms of solving our problem about whether we go to the dark side or not, these are basically the same option, right? So if again we plotted probability and tried to see all of these observations, 2 heads and tails. Sorry, I'm getting very confused with letters. And then tails versus tails. What should we start to see here? each individual coin flip has a 50% chance. But if you look at the outcomes, there's twice as many ways to have one heads and one tails versus both tails and both heads, right? So we would see in this case, if we totaled up the observations, we would see a higher probability of getting one heads, one tails, and the ratio would be about, if we did it enough times, 20 to 50 to 20, 25 to 50 to 25. We still haven't solved the problem. So then we bring in General Grievous because he's got 4 arms, and maybe we can really solve this. Are we ever going to come to a solution? The highest peak's still going to be the 50-50 one, right? And fortunately, we've saved the galaxy because these hapless Sith Lords are spending the rest of their natural lives flipping coins instead of intent on galactic domination. So, but this idea of independent outcomes and probability is important for understanding what we're going to talk about next for NMR. Okay, you'll see the connection in a minute, but we're just going to leave the Star Wars analogy there, hanging out there, unconnected right now to anything else. All right? Why have I wasted all this time? Well, we need to talk about how the magnetic field that proton A experiences is influenced by other nearby protons. We said last time that the field that proton A experiences, which we've called B with the subscript little e, is equal to the external magnetic field, B subscript 0, plus an effect of the induced magnetic field generated by the motion of nearby electrons. And sorry, it's taken me forever. We've said this can either be positive, that is with the field, or negative, against the field. B with the subscript 0 is the external magnetic field that we apply. Right? And that was how we got chemical shift. These things were what gave us, ultimately, the difference in energy, the frequency of the time, the frequency where we can do the spin flip transition, and therefore the chemical shift. And that's great because that gave us information about whether a proton would be shielded or deshielded, whether it's in an electron-rich or electron-poor environment, what kinds of functional groups might be nearby. But it doesn't tell us anything about the connectivity of the molecule. So fortunately, nearby protons influence the field that proton A experiences. Now, we've made up this molecule in this context where proton A is only adjacent to proton B. And there are cases like that. They won't be all of the cases you'll encounter, but this is where we'll begin because it's simplest. We'll say that proton A is on the alpha carbon. A is for alpha, whereas proton B is on the beta carbon. All right. Proton B is itself a mini magnet. It has a magnetic field. And in the presence of this external magnetic field, proton B has 2 possibilities. Proton B can be aligned with the external magnetic field or against the magnetic field. All right? And a proton can't be both ways at once. So when I say that 50% of the time it's aligned with the magnetic field versus 50% of the time it's aligned against the magnetic field, what I mean more precisely is that in 50% of our molecules, proton B will be aligned with the field, and in 50% it will be aligned against the field. That's because of what we talked about last time, where we said this energy difference between being aligned with the magnetic field and against the magnetic field is so small that the population's still basically 50-50. Go ahead.
Is there something inherently within the proton that makes it align, whether
Is there something intrinsic in the proton itself that makes it align with versus less? It has to do just with magnetic forces, right? If you have a large magnet and various smaller magnets, they're going to tend to align themselves with the magnetic field of the larger magnet. It's how a compass works, basically. So yeah, you can think of each proton as a compass, or as a compass aligning with the Earth's magnetic field, only the proton magnet is much, much weaker. Anyway, I'm sorry, that was kind of a rambling answer. Do we basically okay? All right. Nope, not that one. There we go. So in 50% of our molecules, proton B will be aligned with the field, and 50% they'll be aligned against the field. Of course, in any given molecule, it has to be one versus the other. Independent events, independent probabilities, right? So let's talk about how the field contributed by proton B influences what proton A experiences. Basically, the presence of proton B is going to split what proton A experiences into two possibilities. Possibility one is that proton A experiences the external magnetic field plus whatever the induced magnetic field is that either is shielded or deshielded. And then let's say it can experience the influence of proton B. In this case, we'll say plus because this is the one that's aligned with the field. And then the possibility number two is that proton A would experience the external magnetic field plus the induced magnetic field minus the field minus the influence of proton B. In this case, it would be aligned against the field. And if we looked at each individual molecule and totaled up the situation, 50% of molecules would be in situation one, and 50% of molecules would be in situation two. Okay, you with me so far? Proton A, 50% of the time is next to, in 50% of molecules, proton A experiences a field where proton B is aligned with the field. And then the other 50% of molecules, proton A experiences proton B being aligned against the field. Okay, questions? Yeah.
Is there a situation where the induced magnetic field is against?
Is there a situation where the induced magnetic field is against? Yeah, that's why I said this can be positive or negative. I didn't quite know how to communicate that, so yeah. All right. So if there was no proton B nearby, proton A would only experience one possible field and therefore would show up at one frequency, right? But because there are these two situations that are different because of the influence of proton B, overall, our population of protons A experiences two different magnetic fields, two different energy gaps, two different frequencies, and two different chemical shifts, right? So in 50% of our molecules, proton A is going to have a chemical shift that is slightly deshielded. That's situation one, where the field from proton B reinforces the external magnetic field. And then the other 50% of molecules, proton A is going to experience a chemical shift that is slightly shielded. Almost as though if we imagine on this axis number of observations, and on this axis we have chemical shift in parts per million. Without any protons nearby, proton A would experience this chemical shift. We'll say this is the intrinsic chemical shift of proton A. But if proton B, we add that, we're going to have this chemical shift moved in this direction and then in this direction by similar amounts. This is where we are aligned, where B is aligned with the external magnetic field. This is where it is aligned against the magnetic field. Yes?
If we have another atom like chlorine next to the hydrogen A that is already deshielding,
Uh-huh.
does it matter? Like with the hydrogen being that small?
Yeah, it's a good question. If proton A is near something else that's doing some deshielding, does it matter what proton B does? Yes, because the effects are independent of each other and they are of different magnitudes. So we talked last time about how being alpha, a proton on an alpha carbon relative to a chloro group would be deshielded and be in the 3 to 4 ppm region. These shifts, due to the influence of proton B, are very small. In fact, they would be in the hundredths of chemical shift. And they're small enough that in a confusing way, we measure this difference between the two peaks and we back calculate the difference in frequency. And it's typically in the range of 7 to 10 hertz. Now remember I said last time that the frequency that a proton resonates varies from about 600 megahertz to 600.0009 megahertz. Right? That's the range of chemical shift from 0 ppm to about 15 ppm. So that tells you what kinds of changes in frequency are associated with changes in chemical shift. However, the kinds of differences we're talking about here due to the influence of nearby proton B, instead of being in the thousandths place, would be in the millionths place. This would be the 0 to 10 hertz digit, okay? So generally, if, for example, and actually I'll just show you an example of a spectrum. Yeah, that'll work. So we don't need to worry about the NMR spectrum, about what this means other than we've got 3 different kinds of protons. And the chemical shifts are fairly far apart. You've got one at about 1.1, another at about 2, and another at about 4. But each of those peaks, at least 2 of them, are split into a closer spaced set of peaks. And if you measured this distance here and converted it from chemical shift to frequency, that number would be in the 7 to 10 hertz region. All right? Okay, so question so far. I know it's kind of a lot. Yeah?
Let's say we're talking about a hydrocarbon chain. How far away does a proton need to be before it stops affecting the number?
Great. How far does a proton need to be before it stops affecting other nearby protons? Usually beta is it. There are situations where you can be farther away, but for our purposes, directly adjacent is it. Another way of thinking about that is 3 bonds away. Yeah?
So what happens if you have multiple different beta carbons? How does that affect
Good.
that just drastically increase the probability?
Good. So There are some questions in the chat on this issue too. If there were more adjacent protons, would there be even more potential possibilities experienced? Yes. So, and how would that affect things? Well, it, like all good things, depends. So we'll talk about that. Before we get there, we need to define this distance between the two sub-peaks for proton A. Some people call this splitting. Other people call it coupling. Just means that the presence of proton B affects proton A and splits what would have been one peak into two. This difference in frequency we're actually going to define as a coupling constant. And for whatever reason, they have given that coupling constant the symbol J. We'll call it JAB, the coupling constant between proton A and proton B. Sometimes people will put a superscript 3 in front of the J to tell you that it's a 3-bond coupling, that is HA and HB are 3 bonds apart. We won't make that distinction in this class. One of the really interesting things about coupling constants is if we go back and pretend that we're proton B and do the same thing, and we measure a coupling constant for proton B, it'll be the same as it was for A. In other words, the coupling constants are reciprocal and mutual. If proton A is influenced by B to the tune of 7 hertz, then proton B will be influenced by A to the tune of 7 hertz. Okay. So, are we good so far? Do you see how we can take a proton that's just representing, would have been just one peak, and now because there's another nearby proton that has 2 possible orientations, we get 2 different situations for proton A. Yeah? Okay, so let's now deal with the situation where there's more than one. All right, so here's proton A. Now we've got B and C. And let's suppose for our purposes that B and C are chemically identical. Okay? So that means that if there's a coupling constant between A and B, it would have to be equal to the coupling constant between A and C, because B and C are the same thing. All right? Now this is where our scenario with Anakin and Dooku both flipping coins comes in. Let's imagine the situation that A can experience. Situations that A can experience. Remember, 50% of the time B will be up, the other 50% of the time B will be down. Similarly, 50% of the time C will be up and 50% of the time C will be down relative to this external magnetic field. So, situation 1 is that A sees that B and C are both aligned with the field, right? Just like we might have seen that Anakin and Dooku 25% of the time both flipped heads. Literally on Dooku's part, his head went flipping down the street. Situation 2 would be where proton A sees that B is up and C is down, or that B is down and C is up. And since B and C are identical, those two look exactly the same, right? And then the third situation would be proton A sees where B is against the field, as is C. Similarly, as we did with the coin toss, 50% of the situation would be here, 25% here, and 25% here. Now let's talk about what that does for chemical shift. there's two ways we can reason through this. If both B and C are aligned with the magnetic field, that should shift us to higher chemical shift. So if we think about, if we put on this graph like we've done before, sort of number of observations, and on this axis chemical shift, and if we mark the position here where proton A would normally be, then we would expect to see in situation 1 a case where 25% of the time we were shifted to a higher chemical shift because proton A is going to experience fields from B and C that reinforce the external field. 50% of the time, though, those two effects are going to cancel each other out, right? B is against the field, C is with the field, they'll cancel each other out. And then another 25% of the time, B and C will be aligned against the field, which is going to shift the signal for those molecules to lower frequency, lower chemical shift. Situations 1, 2, and 3, 25%, 50% versus 25%. Peaks are present in sort of a 1 to 2 to 1 ratio. All right? Go ahead.
Would those chemical shifts be twice as far because you have the two protons?
That is a fabulous question. I was thinking of that as we were doing this. Would this spacing be twice as far because now you have two? That makes sense, though it doesn't turn out to be the case for reasons I can't explain, so I'm sorry. What you would observe is again a 7 hertz distance here and a 7 hertz distance here. All right. What else? So we call a peak. Go ahead, Byron.
So wait, for example 2, does that mean that the area underneath the peak is just bigger? Or
Yes. So on the y-axis here, we put number of observations. In an NMR experiment, the y-axis will be basically kind of like absorbance, and the area under the peak will be proportional to the number of observations or the number of protons. So sometimes if the peaks are narrow enough, peak height tracks with peak area, so that's what we've chosen to do here. But and in general, just watching peak height, you can recognize 1 to 2 to 1 versus 1 to 1 and so on. All right. So we call a peak that is split into 2 equal peaks, because there's only one adjacent proton, a doublet. And we call a peak that is split into 3 a triplet. So a triplet is what we observe when proton A, for proton A, when proton A is adjacent to 2 identical protons. By the way, if you were to look at either proton B or proton C, what would they experience? What kind of peak would they be split into, if any? I will say one other thing. Chemically identical protons don't couple. They show up at exactly the same chemical shift. There's no splitting. So these are only adjacent to 1 proton, meaning they can only experience 2 different situations, aligned with versus aligned against, 50-50 probability, 1-to-1 doublet. All right? Now, we can go through this analysis all day, but fortunately there's kind of a neat little trick using something you may have learned a long time ago. You may have heard of Pascal's triangle. I'm not even sure if it's called that, but it's a way of getting, I think, polynomial coefficients from x plus 1 to the n power where n is 0 through whatever. And So here's where there are 0 adjacent protons. Here's where there is 1, possibility of 1 to 1. And the number of numbers in this row indicates the number of peaks, and the actual value of the number equals the relative peak intensity. 2 adjacent protons, 1 to 2 to 1. 3 adjacent protons, 1 to 3 to 3 to 1. We call these doublets, triplets, quartets. And sometimes there are situations where there are more. So but you would just continue to, in terms of intensity patterns, to follow the trend of Pascal's triangle down each row of the column, and so on. Once you get out beyond 6, you're getting to the place where there's not that many situations in organic molecules where you can find this kind of thing. Okay. Yes?
I think you might have already mentioned this, but when both of the hydrogens are identical, those two hydrogens, is it a doublet? Or when the two hydrogens adjacent are identical?
Okay. I saw a similar question on the chat, and I was reading it while you were saying that, and therefore I didn't either understand the question on the chat or your question at any level of detail.
Yeah.
So, sorry for multitasking. Try again.
When the hydrogens adjacent to the hydrogen A, B, and C are chemically identical,
Uh-huh.
is it a doublet or a triplet?
Right. When the hydrogens B and C are chemically identical, A will be split into a triplet. Okay? Now, I suppose you could ask the question, and the reason for that is because the coupling constant of A with B is exactly the same as the coupling constant with B and C. Another way of thinking about the doublet is to say, or the triplet is to say, here is where proton A should be. Now we're going to turn on the coupling between A and B. That would be a 7 Hertz difference, and the intensities would be 50-50. And then in another step, we're going to turn on the coupling between A and C. Peak 1 here is going to be split into 2 equal peaks spaced 7 Hertz apart. Peak 2 will be split into 2 equal peaks spaced 7 Hertz apart. These two overlap with each other, and that's where you get the fact that this one is 2 times as tall as this one. So you would see a 1 to 2 to 1 triplet when proton A is adjacent to 2 equal protons, 2 chemically identical protons, or at least protons that have the same coupling constant with proton A. All right, let me make sure. Yeah, Kiana, the triangle is a map of the ratios you would expect for increasing number of adjacent protons, where 1 to 2 to 1 is 25, 50 to 25, yeah. Okay. So, go ahead.
With the doublet, would that be 7 Hertz total distance, so like 3.5 from the center point, or is that 7 from the center point?
7 from the center point, but overall the spread is 14. So I guess, who was it that asked, do you see a bigger separation? The answer is yes, but not from the center point. Yeah.
Okay, so each like gap will always be that 7 Hertz?
Yes, the gap between adjacent peaks in any group of peaks should be the same going from outside to inside.
So if we had we'd have 5 or 6, then we would have a whole bunch of peaks that are all spaced 7.
Right. Yeah, so the more nearby hydrogens you introduce, it's true, the further out the peaks get. But each difference between peaks will be that coupling constant. Now, I've oversimplified by saying that coupling constants are always 7 Hertz. They can be as small as 2 or 1 or even 0. It just sort of depends on the situation. But 7 is a good rule of thumb for the most common situations. Yeah?
There's a question. So on that graph that we drew with like the little dots, the heads,
Uh-huh.
and scale, so we took that from like above, right? Did we make
So in this case, proton A is only adjacent to one hydrogen, and that's where we get the 50-50, but that's not your question.
Okay, so why did we, I was just asking, like, where did we draw that purple one for that example? Do you get what I'm saying?
Say it again, I didn't
So,
quite
like,
hear,
I guess
sorry.
I'm just wondering, like, how did we, when you drew that purple one this time, were you just showing like an example of if there was two different hydrogens? Like, you'd only have three if there was two different hydrogens?
Yeah, so the purple graph was just to show what happens when you have two people independently flipping coins and what the outcomes can be.
Okay.
But that happens to be what we see when two adjacent protons each have two 50-50 possibilities for what they can be, and that influences the third
Okay,
proton. Yeah.
Okay, thank you.
Yeah. Okay, other hands I missed? So now it's going to get really fun because we're going to consider what happens, and somebody in the chat has asked this, what happens when A and B, when the coupling of A with B and C is not equal to each other? It's messy, but it's not as bad as you think, and it's also worse than you think. How can it be both? I don't know. So yeah, let's deal with that. What if the coupling constant, the splitting between A and B does not equal the splitting between B and C? Let me show you a case where that is what we observe. All right, this is proton A, this is proton B, this is proton C. Notice that chemically B and C are not identical. C is cis to the R group, whereas B is trans to the R group. Go ahead.
Sorry, do you mean the coupling constant between A and B and then A and C?
That's right, that's what I mean. Sorry, thank you for that correction. What if the coupling constant between A and B is not the same as the coupling constant between A and C? Yeah. So first, notice that HB and HC are not identical. In fact, we could call them diastereotopic because one of them is cis to R and the other is trans to R, and that's a diastereomer situation. One of the things we observe here is that the coupling constant between A and B is around 15 hertz. Oh, dang it. Sorry, I'm getting wrong all over the place. I'm really sorry when I make mistakes and you have to scribble stuff out. The coupling constant between A and C, which are trans to each other, is around 15 hertz, whereas the coupling constant between A and B, which are cis to each other, is about 10 hertz. That's larger than 7. We'll talk about why that is maybe another time. But let's just imagine what A experiences. And in doing this, it will be simplest if we take this approach that we just barely did for the 1 to 2 triplet at the end. Instead of thinking about all these possibilities, we could take that approach too, but it's going to be clearer for you to see by thinking about, let's start with proton A. Let's turn off all the coupling. There are NMR experiments where you can do that, by the way. Let's turn off all the coupling, and then we'll turn them on one by one and see what happens. All right? So let's put proton A here. And we're going to, at this stage, turn on the JAC coupling 15 hertz. And let's keep things consistent by, let's let each of these squares equal 5 hertz or something like that. So 15 hertz would be 3 to this direction and 3. Oh, I messed up. So each square distance is, I think instead of 5, I meant 2.5 hertz. Sorry. Anyway, This distance here is 15 hertz, and I'm trying to do it to scale. That's the point. Don't get lost in all the mistakes and details. With me so far, we've turned on the coupling between A and C. That's the trans coupling, right? Now, let's turn on the coupling between A and B, which is 10 hertz. Each of these peaks that are separated by 15 hertz are themselves going to be split by 10 hertz. Now, because the coupling constants between A and C and between A and B are different, I'm going to copy down our triplet to try to show you why we get this different result. Before, with the 1 to 2 to 1 triplet, coupling constant between A and B was equal to the coupling constant between A and C, so that by the time you did the second splitting, those two peaks overlapped with each other. If the coupling constants aren't equal, the two inner peaks don't overlap with each other. They separate out. And what you see is what we call a doublet of doublets. You have these two doublets that are themselves separated by a coupling constant. And in that case, the ratio of lines would be 1 to 1 to 1 to 1. The reason we see this instead of seeing a triplet is that the coupling constant between A and C is different than the coupling constant between A and B. Yeah, Luke.
Is the coupling constant just going to be given to us, or is that something that we have to calculate?
Will coupling constants be given to you? Generally, you'll be looking at a peak that has splitting patterns. If you wanted to, you could measure the coupling constant, but for the most part, you're going to be using the shape of the peak itself to figure out how many protons are nearby. And then, yeah, sorry, I missed. What would happen if you had turned on AB first? You can totally do that. Just real quickly, if we turned on AB, which is equal to 10 hertz, we would get two peaks spaced. Sorry, we need dotted lines. This far apart. And then you turn on AC, which is 15 hertz. This one's going to spread out, and we say by 3 squares. And this one will spread out by 1, 2, 3 squares. So you get exactly the same situation. Yeah. Other questions? Yeah.
So you said that protons on this connected to the same carbon don't couple, like they don't have an impact?
What we said before was that B and C, because they're identical, didn't couple.
Yeah.
So are you asking, would they couple here because they are different?
Yes.
Yes, they would.
Okay.
Yeah, and that's a interesting feature of olefins in general, is that protons that are on the same carbon in olefins that are monosubstituted aren't identical to each other, and they can couple. There is a coupling constant between B and Z that is not equal to 0. I forget what it is. I think it's less than the trans and the cis coupling. Yeah.
And just to follow the question, so why do they not couple when it's not?
Why do they not couple when they're identical? I don't know. I think it's a technical issue that has to do with the NMR experiment, but and the fact that you're irradiating the proton. I mean, if you think of the NMR experiment, it's not this simple as we're dialing the frequency up, and we get to this point, and we see absorbance of that frequency. Remember, at that frequency, you're causing spin flips to happen. And so at that point, you disrupt the populations as to whether it's 50-50. And that's a terrible explanation. It's probably based in some physics that I don't understand. One of my colleagues said, you know, I tell my students anything that doesn't make sense about NMR is the physicist's fault. But we're in the same college with the physicists, and they're our friends, so we won't blame everything on the physicists. We will just shrug our shoulders and say, they're just smarter than us, and and I don't understand. All right, am I missing some things on the chat? For what we talked about before, A doesn't have to be the same as B and C, does it? Not sure I understand. A is chemically different from B and C in this case. We've said in this example, B and C are identical to each other. In the one we just did, A is distinct from B and C are actually distinct from each other. All right. So let's actually just look at some data and start to propose some hypotheses as to how many protons must be near or adjacent to how many protons must be adjacent to the proton represented by a peak. We're still getting some questions in the chat. Do the protons have to be identical to couple or not? Let's be clear. B and C do not couple with each other. In other words, the coupling constant between B and C equals 0. A couples with B and C, and because their coupling constants are the same between A and B and between B and C, we observe that triplet pattern. The issue with the alkene was that when we get down here, B and C are not identical anymore, so they could couple with each other. Yeah?
So with the first one, A will experience a triplet, but B and C will both experience doublets?
That's right. A would experience, we would see A as a triplet. B and C would be a doublet, because B and C each only experience one nearby proton. In contrast, for this example, A is going to be a doublet of doublets, but that will actually be true for C and B as well, because C will be split by A and B will be split by A and C. Okay. So let's just look at some data. Here, we're not going to worry about chemical shift, and we're not even going to worry about how many protons are represented by these peaks. As we consider each peak, you will think of it as proton A, and then we'll be asking, what do the peaks tell us about how many protons should be nearby? So you see this closely spaced group of peaks. You zoom in and you see it's roughly a 1 to 3 to 3 to 1 ratio. There are 4 of them. So we would call that a quartet. Now we can go back up to the Pascal's triangle, find where we see that 1 to 3 to 3 to 1 quartet, and that tells us how many protons are nearby, right? 3. So we would say for this peak that whatever proton A is, A must have 3 adjacent protons. We don't yet know whether those protons are chemically identical as they would be in a methyl group, or they are 3 chemically distinct adjacent protons that just happen to have the same coupling constant with A. Yeah, question in the back. Okay. But a very common situation for having 3 adjacent protons that are identical is what? If you think about hydrocarbons, what situation would you be in where you have 3 identical protons adjacent to you? That could be a methyl group, right? A could be adjacent to a methyl group. All right. Now we're getting some connectivity. And then similarly, we could look at these peaks. This one is not a doublet or a triplet, it's just a singlet. That's informative. That tells us there are 0 adjacent protons to whatever this peak represents. This one's a triplet, that says there are 2 adjacent protons, okay? So you can use this to get clues about connectivity. We unfortunately have to leave it there. But next time we'll get to solving the structures from this information.